This video is focusing on orbital diagrams, which is another representation of the electrons in an atom, except this time it's more of a pictorial representation of electrons in the atoms, so more of a picture. This picture represented here is one of the fancier ones that I've seen with the color and the circles, but it's absolutely correct. What I'm going to actually show you is a more simplistic version of how to actually write it out, so I don't have to worry about perfect circles and coloring. Each circle represents an orbital in an atom where electrons can be found. I'm going to go back to our analogy of the hotel for our atoms. Keep in mind that the floor of the hotel was the main energy level or the main shell. The rooms on those floors are the subshells or sublevels. And so now the orbitals are like the beds in those rooms. And more often than not, it's common to have 2 people per bed. And it's similar here in that we have 2 electrons per orbital. For example, if you look at all of the S subshells, they each have 1 circle, 1 orbital. And that's because 2 electrons can fit in S and 2 electrons can fit in 1 orbital. So we only need 1 orbital. However, in P, we can have 6 electrons, so we need 3 orbitals, 2 in each one. Similar for D, in which we can fit 10 electrons, we would have 5 orbitals. And for F, where we can fit 14 electrons, we would have 7 orbitals. The way we represent electrons when we do orbital diagrams is with arrows. And it's your choice. Oops. It's your choice whether you draw your arrow as a full arrow. I personally just draw a half arrow. But again, that's up to you. So the easiest way to do this would be with an example. So if you follow along on your periodic table, we'll look at chlorine, which has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. Okay. So we're going to start off with our arrow pointing upwards. If you look on this one, let me erase some of my green marking. That arrow pointing upwards represents energy. Okay, and so we've already discussed that the lowest energy is going to be at 1s. So that's why electrons always start at 1s. They're lazy. So they want to fill the lowest energy first. So I have my arrow with energy representing the energy. And then I'm going to go ahead and start drawing my orbitals. First begin with 1s, which is the lowest energy. And again, it's s, only 2 electrons fit, so I only need 1 orbital. Then I have 2s. And then I have 2p, which has 3 orbitals for the 6 electrons. And notice they're on the same level, which means they all have the same energy. And then I have 3s and 3p. Okay. Then the next, we're going to start filling in our electrons. And again, we show our electrons as arrows. Again, you can either do full arrow or half arrow. I do half. In 1s, we have 1, 2 electrons. 2s, 1, 2 electrons. In 2p, we have 6 electrons. 1, 2, 3, 4, 5, 6. In 3s, 2 electrons. 1, 2. In 3p, 5 electrons. 1, 2, 3, 4, 5. And that would be the orbital diagram of chlorine. Now, if you notice, there was a particular way that I was filling in these orbital diagrams. And I was following 3 specific rules that go with orbital diagrams: the Aufbau principle, Hund's rule, and the Pauli exclusion principle. Aufbau principle you already know even if you didn't know the name. And the Aufbau principle just states that the electrons fill the lowest energy first. Energy first. Hund's rule is more specific to as we're drawing the orbital diagrams, and it deals with those that have multiple orbitals, for example, the p's. If you remember, I filled them 1, 2, 3 singly before I paired them up. That's what Hund's rule states. It's kind of like the beds. If there's 3, or if there's people in a bed in a room and there's these beds there, you're going to want to each have your own bed before you have to share. That's kind of what the electrons do. So the electrons will be single before pairing up, single before they mingle. The Pauli exclusion principle was with how I drew the arrows. If you notice, 1 up, 1 down. The up and down, the direction of the arrow, represents the spin of the electrons. Pauli exclusion principle states that if the electrons share an orbital, they have to have opposite spins. So it's like if you're sleeping in a bed head to foot with a person. Opposite spins. So I'm going to do one more example with you guys. I'm going to do carbon, which has the electron configuration of 1s2, 2s2, 2p2. So I'm going to draw my arrow for energy. 1s is my first orbital, 2s, and then I have 2p. And I'm going to draw my electrons in 1s, 1 up, 1 down, 2s, 1 up, 1 down. In 2p, I only have 2 electrons. But if you notice, I have 3 orbitals there. That doesn't mean that I erase that third one, as it's not necessary. That's like requesting a hotel to take a bed out of the room just because you don't need it. So those 2 electrons, since there's the beds, since there's the orbitals there, they each take their own. So they don't share. And again, that third one just stays empty. So now what I'd like you to do is I'd like you to think about your birth date, the day of the month that your birthday falls on, and I want you to use that as the atomic number. On a separate sheet of paper, write that element, write out the electron configuration, write the shorthand electron configuration if you can, and then I want you to try to draw the orbital diagrams for that atom.